Hello everyone, and once again welcome back to the fundamentals of particle and fluid solid processing. We were discussing on the particle size reduction, and in particular we were on the particle fracture mechanisms. So, we have now understood that the ways of particle fracture that can be introduced. So, there was or there is a elastic limit, and we have to come across that elastic limit to introduce the fracture. Due to the irregular surface in realistic cases, the applied force or the intensity has its stress distribution on the surface of the solid particle. Now, once it breaks down, this application of force then shifts, and presence of any crack actually results in stress distribution on the in the particle, and this change in crack length as it propagates, it results in stress distribution and the energy content in the solids. The most of the energy that is supplied for size reduction is consumed as to affect the particle plastic deformation, and this plastic deformation is a necessary step before the fracture to occur. So, it has been seen that it is really difficult, that several experiments are done, and this schematic shows which are again not to the scale, but on the y axis it says the compression strength, and here in the x axis it shows the diameter of the particle. Now, to break a 5 micron particle of quartz glass compared to 100 micron particle, the increase in the amount of compressive strength is significant. And it is true for most of the material. It has been seen in practice for several materials. So, typical hypothesis is that there are flaws in the materials, and these flaws in the particle changes with their size, or say if you can introduce some flaws, some fractures, in general this can be called as flaws, this fracture or deformation or something else, it changes with the size, and the weakest flaws progressively eliminated with the size reduction. The most vulnerable parts are eliminated, or weaknesses are eliminated as the size being reduced to finer sizes, and that is why the reason is that the finer particles are really difficult or very hard to break to even finer particles. It has been seen that this capacity of storing energy in a particle is proportional to its volume. The energy requirement for propagating a geometrically similar crack is proportional to its surface area. As the surface area increases, the energy requirement for propagating several cracks which are similar in nature also increases, and the energy available per unit crack area linearly increases with particle size. And so, that is why the large particles are easier to break than the fine particles. So, several reasons or several hypotheses have been postulated on this reason, that why the finer particles are hard to break with supporting theory. So, this compressive force introduces small flaws, and the energy concentration, if it increases or exceeds beyond a certain value, then the flaws will grow rapidly, it branches and the particles break up. And in assembly of particles, the probability of this fracture increases with the number of contact points between the particles. When the rate of application of this force is another important parameter, because the time lag between the attainment of maximum load and the fracture exists. So, what does this mean? It means that a small amount of force or a smaller force can cause fracture provided it is maintained for sufficient time. This rate of application is one of the vital component in size reduction when it comes to the efficient processes, because this is one of the vital parameter, that time lag, there is a time lag between the attainment of maximum load to create that fracture. So, does that mean that if you have a sufficiently higher load, cannot it create a fracture? Yes, the greater the applied forces are, the process is more and more less effective in energy utilization. It becomes an inefficient process as you increase the applied load, on the contrary to the general belief that I have a very huge impact, I make it on the solid rock, and that is the process that is done. It is the most inefficient process, because the amount of energy that you are supplying is not being converted into the creation of surfaces, new surfaces. So, greater rate of applied load, the less effective the energy utilization, and high proportion of fine material that are produced. Because if you remember the initial thought experiment, that you had a lump of material, you had an impact, the type of particles that we got, that we initially had very coarser particles in numbers, then the intermediate particles, and very few of the finer materials. So, when the intensity is increased, the solid particles basically breaks into small pieces, and the number of fine particle count goes up, but the size of the fine particles does not change. So, in terms of these finer particles, there is no such new surface creation is happening. So, that means an interesting comparison, say you have a falling mass and there is a slow rate of hydraulic pressure that is impacting a certain material, in which case you would expect that the more surface would be created. It is the latter one, that is the slow rate of hydraulic pressure. It can create even 3 to 4 times more surface, which could be produced by a single fall of a mass on that object. So, this is the efficient utilization of energy that is being supplied. But in case of viscoelastic materials, high rate of force application is necessary to create the fractures. So, for viscoelastic material we need really high force, but typically for the common materials or the other materials, when you have a impact, the rate of impact is what matters, and so the method of application of this force. Along with the load application time, the methods of application is also important in size reduction in order to achieve different or desired size range of the product. So, those methods of applications are, say, impact, compression, shear and attrition. Now, in most of the cases, on most of the equipments, it is very difficult sometimes to say that which one is the dominant mechanism that it is using or by which this thing is happening. But still the equipments are broadly categorized based on these typical methods of application. And again, sometimes, as I said earlier, that not a single type of application is sufficient. Sometimes we need a hybrid of those, and certain instruments or equipments actually use such kind of thing. So, impact is basically comes from a single rigid body, kind of a hammer, okay, on a solid, say, coal. You break into pieces by hammer, that is the impact. The compression, say, in the same coal particle, you compress it from the two rigid body, from the two sides by two rigid bodies, and creates smaller coal particles. Shear is happening between the fluid solid particles or the shearing action. A jet of, say, water, you have held the coal particle against in a certain single frame or fixed frame, and the water jet hits that coal particle, say. So, again, you can think of that is also kind of having the mixture of impact, the impact with a certain velocity, as well as when the fluid flows across this, it creates shear. When it comes in a confined spaces, it creates shears, it creates wears on the surfaces, and it breaks into small pieces. And the attrition, that also happens with the particle-particle collisions or solid particles collision, or the solid surface or the fluid particle collisions. So, when we will talk about different types of equipment, I will try to highlight that which mode is basically being applied there. So, that brings to the point that now we have to estimate what is the energy requirement of such equipment or such processes of size reduction. There are three main laws or postulates. One of such, the first one in chronological order, is the Rittinger's law. He proposed that energy required to create this new surface was directly proportional to the area of new created surface. That means, say, we have initial and final particle sizes of x1 and x2. The volume shape factor is Kv, which is independent of size, we assume, and it is the logical assumption. So, the volume of initial particle Kv x1 cube and volume of final particle is Kv x2 cube. So, from each particle of size x1, it would result in x1 cube by x2 cube number of particles of size x2. If we also assume that the surface factor surface shape factor Ks is also independent of size, then the new surface that are being created is nothing but this total expression, this complete expression. The x2 is the product, the newly created product step, which is the size of x2 is the size of the final particle size, and x1 is the initial particle size. So, the surface area created is this expression. Now, this can be rearranged to be written in this form. This x1 cube, if we take that in common, it results in this expression. If we convert this to the new surface created per unit mass of original particles, that means this is the surface area multiplied by the number of original particles per unit mass, and that is this expression. If we have to now remember the initial classes, so this is the number of original particles per unit mass, which can be written in this form. So, which means this newly created surfaces, the energy requirement is eventually dictated by this parameter 1 minus x1 divided by x2 minus 1 divided by x1. So, as per Rittinger's postulate, the breakage energy per unit mass of feed E is equals to a constant term, because we have assumed Ks, Kv to be independent of the sizes. Rho p is the density of the particle or the solid material, which gives the Rittinger's law expression. This is one of the vital expression and you have to remember. So, here Cr we call it as Rittinger's law constant. But this in differential form can be expressed in this way. But in practice, this energy requirement is usually several order lower than what is there in practice. So, the practical energy requirement is 300 to 400 times higher than what Rittinger's law provides or determines. So, that means it is unlikely that the energy requirement and the surface created, these are related, because this 1 by x square is nothing but the surface creation, new surface creation. So, Rittinger's law dictates or basically tells that the energy requirement is proportional to the new surface creation, but the amount it dictates, it grossly under predicts. So, from 1867 to 1885, in 1885 Kix proposed that the required energy was directly proportional to the ratio of the volume of feed particles to the product particles, based on his calculation on the stress analysis for plastic deformation. So, that means that if we go back to our example, that say we have the initial feed size of x1, final particle size of x2, then the volume ratio is x1 cube by x2 cube, assuming the shape factor is constant. The size ratio x1 by x2 basically influences this x1 cube by x2 cube. It eventually dictates this volume ratio. So, Kick's law says the required energy was directly proportional to the ratio of this volume of feed particle to the product particle. That means, in other way, it is the size ratio. So, if del x1 say the change in particle size, so that means x2 is nothing but x1 minus del x1. So, this size ratio is basically the del x1 by x1. This is what influences the size ratio. The change in particle size with respect to the original particle size. It determines the energy requirement for particle size reduction from x1 to x1 minus del x1, which we considered as x2. So, as this Kick's law says that this del E, this energy requirement, is basically proportional to this parameter, this ratio, where Ck is the Kick's law constant. And in the limit of del x tends to 0, the Kick's law in differential form becomes d by dx is equals to Ck 1 by x. If we integrate that, this is the integral form. E is equals to Ck multiplied by ln x1 by x2. So, which means that in order to improve the Rittinger's law predictions, Kick came up with these expressions. Now, this from surface area creation, this has become the size ratios of the initial and the final particle. X1, this is x1 by x2, which is the initial particle size by final particle size. And earlier in Rittinger's law, it was dealing in the differential form of the surface area 1 by x square. Now, even then this Kick's law provides some unrealistic value, because now it is dealing with the size ratio. So, what it says that the if irrespective of the particle size range that you are trying to have the size reduction, if the size ratio is same, then the energy consumption would be same for a same material. This is what it tells, that if somehow x1 by x2 is fixed or constant, the energy requirement is similar or same, but that does not happen. Say from 10 micron particles to 1 micron particle, the amount of energy that would be required, and from 1 meter boulder to 10 centimeter block, this is not the same amount of energy that would be required. So, the point is that the range of experiments or the range of data that has been considered in Kick's law is not enough to have the predictions for the all size ranges. So, the extrapolation of data that has been gathered for these large product sizes to predict the energy requirement, okay, that does not necessarily tell that would be the requirement for the smaller particles as well. It does not work, this simple extrapolation does not work, because we have seen in the fraction mechanism the breakage of finer particles. The finer particles, it is the characteristics forces of the material that retains its size. We have to overcome those interactions or attractions. So then again, Bond in 1952 came up with more generic form of the expression of the energy requirement, and which is widely used as an initial estimation for the energy requirement. He proposed that instead of just 1 by x, it is varying 1 by root over of x2 minus 1 by root over of x1 multiplied by the bond law constant. But most common form of Bond's law is this one. So this EB is equals to Wi multiplied by 10 root over of x2 minus 10 root over of x1. This is the most common form of Bond's law, where EB is the energy required to reduce the top particle size of the material from x1 to x2, and Wi is the bond work index. So this top size, how do we define top size? It is not easy to measure top size. So these x1 and x2 are basically the sieve sizes in micron through which 80% of the material in the feed and the product respectively can pass. And this law particularly has stressed on this 80% of the material to be passing through. And Wi is the energy required to reduce the particle size of unit mass of a particle from infinity to 100 micron. But again, this is a definition, theoretical definition, that Wi or the work index is the energy required to reduce the size of unit mass of a material from infinity to 100 micron. But how do we measure that? Typically, it is assumed to be independent of final product size, and these are measured empirically in laboratory experiments. Even EB and Wi, the energy required for this breakage, and work index both have dimensions of energy per unit mass, and popular unit in industry cases are this kind of unit: 1 kilowatt hour per short ton, and that is equivalent to 4000 joule per kg. And work index parameter, this has to be experimentally determined. For example, for bauxite, these are the values of this work index with this unit, kilowatt hour per short ton. So this Bond's law actually provides the reliable fast approximation for the energy requirement for the product size not lesser than 100 micron. And in fact, it has been seen, and in fact it is there, that most of the practical industrial applications works in this range, not below 100 micron or so, handling the solid particles. So this Bond's law is widely used, and in differential form, the Bond's law gives this form, that d by dx is equals to Bond's law constant divided by x to the power 1.5. So, what we have learned today is that there are 3 laws to calculate the energy required for new surface creation: Rittinger's law, Kick's law and Bond's law. We have seen their limitation. As per their development, as per their shortcoming of the Rittinger's law, Kick's law was provided, but again that was not sufficient, so Bond's law is provided, which works pretty well as a first approximation for the design purpose. We will see one problem related to this energy calculation in the next class, and we will also see couple of equipments that is required or how it works in the next class. Until then, I thank you for your attention and see you with the next class.